Okay, so last time we started. Okay, by the way, as I said yesterday, um, we are not going to do this appointment procedure anymore. So I am expecting everybody to come to class face to face because the regulations or the Ministry of Health say that we don't have these kind of restrictions anymore. But in closed environments, we should keep our masks on. So if you don't have your masks, just find somewhere one face mask. So let's keep this for a while. Let's be careful. Keep the windows open during the break time or during the lectures, whatever. And we'll go that way. So I am expecting everybody to attend the courses face to face. Okay. And I was expecting lots of more people today for some reason. I don't know. I mean, what happened? It was more crowded than this if I when I was taking the appointment-based kind of attendance. Anyway, it's your choice. So we talked about the processes. We said that, okay, the idea of the process is the basic idea of the operating systems actually, and on top of this, all the rest of the operating system concepts are built. And at the bottom of the operating system, we have the scheduler. That's the most basic level. Scheduler of the processes. This scheduler is a simple algorithm that makes a decision on which process should use the CPU now for a given point. As I said before, operating system is a piece of software, and scheduler is part of it, and scheduler is of course a piece of software. Very simple, very small piece of software most of the time. It has to be simple because we run it very often. Okay, between each process, we run the scheduler, and the scheduler makes a decision. Usually the decision is just who is next in the queue. Okay, plus on top of it maybe some other stuff, but it has to be very, very simple, very, very fast. Otherwise, this would take lots of time to make a decision, and that would make our overall system very inefficient. It's spending too much time for scheduling decisions. Okay, so scheduling chooses one process from the page table. Okay, page table is an array of structures, and it keeps information for the processes. For each process, there is lots of information being kept, and some of them are like as simple as all the copies of the registers while the process is blocked or in the ready queue. Also, the status of the open files, the list of open files, its memory configuration, it is priorities, it is privileges, and etc. Many things, and in fact, this table gives us a good idea of what kind of things could be in a process table, depending on the operating system, of course. We know this much, registers, etc. Okay, for Unix, maybe it is parent processes, process group, etc. Again, for Unix, there are signals and the timers and etc. For memory management, okay, where is my memory, where is my text segment, where is my text segment? For the file management, the list of open files and their status, etc. These are all kept in the process table, which is a important section of the important section of the memory for the operating system. Obviously, this process table has to be kept in the kernel memory area. Nobody should have access to it other than the kernel mode. It is protected. If it is not protected, then somebody can accidentally or by on purpose can see it, can modify it, which would not be a good thing for us. It would cause either instability in our system or security problems, right? If everybody is accessing whatever they want, that would be a bad security problem. So we talked about those. So I think this is the place where we stopped last time. let's continue from this position. So you started on Thursday night or Friday night, I don't know. Our TA Gizem gave you a problem session online. She talked about the inter-assembly language, right? And she gave you the pointer for that guy's write your own Linux operating system videos. So keep watching those videos till the end. So basically we are going to use those videos as our base operating system, and we are going to write our schedules and the memory managers on top of that code, maybe some modifications. Okay, so watch all those videos and implement them, especially before the homework start. Build your own working environment, that virtual machine, so that you don't have to boot up your computer all the time to test your operating system. How many people did that virtual machine? Did you guys did the virtual machine for that operating system? Nobody? How many people watched the first two video? So one, two. So the rest. You guys know what I am talking about? How many people attended Gizem's problem session on Thursday? So she gave you the link for the where is my okay, here it is. Yeah, okay. So she gave you the link for the write your own operating system video series by this guy. I am sorry for this guy, but I don't know his name. I keep forgetting it. Okay, so the first lecture or second lecture, he says that it is difficult to boot up your computer with your new operating system all the time because lots of crashes and everything. It takes time. So he builds a virtual. He uses a virtual machine and puts his operating system on that virtual machine. That makes the things a lot easier because booting and testing stuff is as easy as writing an C program, etc. So build that virtual machine and get that virtual machine and put your operating system on top of that virtual machine. We are going to test your homework submissions using that virtual machine because. Okay, it looks like nobody understands what I am talking about, so watch that video and build your own environment to develop those stuff. Okay, good. So let's move on from this point and let's continue with the. We keep talking about this. We keep talking about this switching between the processes. We keep talking about making scheduling decisions and etc. Let's look at in detail what happens when an interrupt happens in terms of software. Well, we don't care much about the hardware, what's happening with hardware, but sometimes we have to look at it to see what's going on. We can't do anything about the hardware, but we need to know it. So suppose that my program is running and a disk interrupt has happened. Okay, why would a disk interrupt can happen? Well, it can happen because I ask for some data, and this controller says that your data is ready. Okay, your data is ready in my buffer. Here is my buffer. Inside this controller's buffer, your data is ready. So this interrupt controller, I told this into interrupt controller, which is a device connected to my bus, and the interrupt controller tells the CPU that there is an interrupt happening. So stop whatever you are doing. Okay, you need to take this interrupt, and for that interrupt, of course, we know that the operating system has to have a interrupt procedure. So let's look at that one. So as soon as the interrupt happens, Okay, as soon as the interrupt happens, these two things are done by the hardware. The rest of them are done by the software. Okay, the hardware immediately stacks the program counter. It saves the program counter on top of the stack, and the program status word and some of the registers, but not all of them, not all of them, because you need to be careful here, because every time the interrupt happens, you don't want to save all of your registers, because that might be too expensive. Okay, so you need to be careful here. And since this is hardware says that I am going to do only the minimum. Okay, only the required ones, not the rest of them. So without saving the stack pointer, it's going to be a problematic, or the program status word, or important register. Okay, and then hardware, okay, loads the interrupt, loads the program counter, that is the entry point for the current interrupt, from the interrupt vector. So there is an interrupt vector somewhere in the memory defined by the operating system. Okay, and the hardware knows that location. How does the hardware know it? Because operating system programmed the hardware previously when the computer booted up. Okay, hardware gets the address of the interrupt handling routine from that interrupt vector by getting this information from the interrupt controller. Interrupt controller says that, okay, you get the interrupt number 7. Okay, interrupt control tells this to the CPU. Okay, and the CPU, as the hardware, knows that interrupt number 7 has happened. So I need to look up the interrupt vector and find the interrupt number 7, and at that position I have the function pointer to handle that interrupt number 7. Okay, and that's all the hardware does. So I have a now address in my memory that is the address of a function that will handle this interrupt. Okay, so that's a function written in assembly language. That assembly language function starts and it says that I am going to save all the registers now. Hardware save some of them, but I am going to save the rest of them. Okay, I saved all the registers, and I save them. Where do I save them? I save them in the process table, of course, because I interrupted the process, right? The interrupt was running, and I interrupted it. I saved all the registers. I had saved all the required data on my process table. And then says that, okay, something new is starting, that new thing needs the new stack and required memory area, and it sets up that piece of memory as the new stack and the local variables and etc. And these are all done in assembly language, actually, because I mean these 3 and 4 we are talking about saving the registers. We are talking about taking a backup of all of your CPU registers, etc. I don't have any functions to do that in C programming language. This has to be done in the assembly language. So this part of the operating system is written in assembly language to save all of that stuff. And then after everything is saved, I can run my C interrupt service routine. Okay, it knows what to do. Okay, that one says that, okay, I know what to do. I am going to take these bytes one by one, and I am going to put them. Okay, this is my memory. I am going to put them one by one to this location. That location is already given by me with the function read. Okay, I am going to do this one by one. Okay, and that's what this interrupt service function does. Okay, reads the data and puts it in there. So it is done. I handled the interrupt. So what am I going to do? I can go back to the original process that was interrupted, or I am the operating system. I need to make a decision now. Should I go back to the interrupted process, or should I choose a new process That's what the scheduler does actually. So its scheduler is running here. Okay, scheduler runs and makes a decision. It says that among all the processes that are ready to run, I am choosing this one based on my scheduling policy. What is my scheduling policy? I don't know. It's something generic. So we are going to look at the scheduling algorithms later. But usually the simplest one is whatever waiting in the queue. Okay. So I choose that one. So I know where to return now. And the C procedure returns the assembly code again. It says that, okay, I'm done. Assembly will take care of loading all that data back from the process table. Okay, so I am going to get all the register values back from the process table, but those register values will be obtained from the chosen process table entry, right? Because the scheduler said that, okay, in the process table, item number 7, you are going to switch to that one. So the assembly code takes all that information from there and loads them carefully into the registers, and then it tells the hardware that, okay, we are done running the interrupt service procedure and the scheduling. Now we can go back to the user mode with this register data, including the program counter. Okay, and after that our normal program starts running. Okay, so that's what happens when the hardware interrupt happens. Okay, any questions on this? Where is my attendance sheet? Any questions on this implementation of the processes? So we looked at this picture actually previously, but not in this detail. Now we are looking at in this detail. And this is a hardware interrupt. We looked at what happens when the software interrupt happens. That is the system call. System call is no different than this actually. The cause of the interrupt is not the hardware, but this time software. You say that I need to read some data from the disk. Okay, this is the procedure number 11, for example. Now handle this, and then hardware automatically traps it to the kernel, and kernel starts running, and it handles it, and the rest of them is almost the same thing. Okay, so in order for the operating system take over the CPU, either these steps has to happen, or the software interrupt handling steps has to happen. Okay. So before the scheduler runs, before the scheduler decides which process to run next, lots of stuffs are being happened. We are saving stuff and etc. So if this one and this one and this one and this one, if these 4 takes lots of time to do, taking a backup of that, all that kind of stuff, that's the context switch time. Okay, that's the cost of an interrupt. That's the cost of making a system call. Okay, that's why sometimes it is too expensive. You might say that what is so expensive about saving a few registers? Well, it is not that expensive, but if this thing happens millions of times a second, that's going to get lots of CPU time. It is okay if this one happens maybe 40 times or 50 times a second. That's okay, but if you keep doing this a lot of times a second, then that's going to be a problem. Context switch time is going to give you lots of trouble. And when you do this, actually, since you are switching context, since you are now running a different program than the original one, your cache will be invalidated, and you're going to get lots of cache misses, and cache misses, as you know, are very expensive. Okay, good. There are no questions, then I'm going to continue. No questions. Okay, let's look at this one. Let's look at this, how much we are gaining by doing this multi-programming. Okay, let's say I have a I/O intensive job. What is I/O intensive job? I/O bound job. Sometimes we call it that way. Say that my process P1 says that it spends 80% its time waiting for input output. Okay, you say that, okay, I'm going to get some data from the disk. I am going to send this data to the network. I am going to wait for some data from the network, and etc. So most of the time, 80% of its time, it is waiting for something happening. Okay, so if this is the only process on my system, then I am only 20% efficient, right? I mean, because this process cannot keep the CPU 100% busy. Okay, even if it is the only process that can use the CPU, it has to wait 80% of the time for some input-output stuff. So that's why we invented multi-programming, right? We said that if my computer is multi-programmed, okay, I can have 2, 3, 4, 5 processes at the same time. If this P1 is waiting for input to happen, then I can let the P2 take the CPU. And if P2 is busy, if P2 is again waiting for some input, then there is P3 and etc. Right? So let's look at this two process stuff. Okay, P1 and P2. Let's say P2 is doing the same thing too. Okay, 80% of the time, it is waiting for input output. Okay, so that means what? 20% of the time my CPU will be busy for this one, 20% of the time my CPU will be busy for this one, but I cannot add them together, because what if both of them are waiting for the input? So what are the chances that both of them are waiting for the input? It is 0.8 times 0.8, right? So it is like, is this correct? So 64% of the, right, is that correct? So 64% of the time they are both waiting for the input output IO, right? So I made the things a little bit better. Why? Because now I am 36% efficient, because 64% of the time I am waiting for, both of them are waiting, right? So I mean, this is, I mean, multiply these two probabilities, that will give you both of them are waiting for some input output, right? So 64% of the time I will be waiting for input output. So let's make it better. Why don't I make this 3 processes? 3 processes. If I make this 3 processes, do this calculation. What is this? 8 times 8 times 8. What is it? What is 8 times 8 times 8? Everybody is holding a cell phone. Why are you holding that cell phone? 0.5 for 1. Okay. So it looks like 50% of the time now I am waiting for the input output, right? So much better. So I can keep my CPU busy half of the time now. So what is the idea? Put more processes in your memory, and that will make my efficiency times a little bit happier. So the rule is, maybe just do this: 0.8 over n is my IO wait time, and if I take this 1 minus 0.8 over n, that will give me my efficiency. But 0.8 is my only one example for the processes. How about this one? P is my IO wait time, right? P is my IO wait time. P to the n is all of my processes are waiting for IO at the same time. And if I subtract this number from 1, that will give me my overall efficiency. That will be my CPU utilization. 1 minus P to the n. Okay, that's my overall efficiency. Of course, I have a very simplistic approach. I assume that there is no switching cost. between the processes, right? That's what I assumed. And also I assume that all of the processes are the same. They are all p% idle. Because most of the time they may not be p% idle. Some of them are 80% of the time they are waiting for input output. Some of them are 30% of the time. Some of them are different, right? So, but I mean, this is just a simplistic case. We are trying to model the efficiency of multiprogramming using some kind of a closed form mathematical formula, CPU utilization. If I have this formula, I can do some experiments, some maybe fun experiments, for example, like this. This curve is for P is equal to 80%, okay? So if I have a single process, my efficiency is 20%, right? If I have, that's what I'm talking about. If I have two processes, my efficiency is 40%. Three processes, my efficiency is 50%. If I have 10 processes, my efficiency is almost 100%. It cannot be more than 100%. So load more processes to your memory and you'll get more and more efficient, right? More and more efficient. Okay, so for 10 processes, you are not wasting any CPU time. Even if each of your processes are only 20%, they can utilize the CPU only 20% of the time. And this curve is for the 50%. P is 50%. That is, each process can use the CPU's time for 50% of the time. This one is much steeper. The processes are using 80% of the CPU time, each of them. So only two processes can utilize, like what is it? 16, I think 85% of the time. How do I calculate this? This is okay, 20. 2 times 2 is 4, yeah, with 96%, right? Yeah, only two processes can take 94%, 96% of the CPU time. So these are some results out of this simple formula 1 minus p to the n. Okay. Of course, if p's are not equal, that is, if I have 3 processes, the process number 1, let's say, takes 80% of the I/O time. Process number 2 takes 20% and 40%. If I multiply all of those, and if I do this 1 minus thing, that's going to give me the efficiency for my overall system. Those p's, they don't have to be equal to each other, so they can be different. So 1 minus 0.8 times 0.2 times 0. Let's say 5. So this is 20% efficient, this process, 80% efficient, and 50% efficient. The nice thing is that each of them is less than 1. So if I multiply many of them, they can go as small as 0, or they can go as large as 1. So this number will never be less than 0, greater than 1. Okay, good. Very simplistic approach to see what kind of utilizations I would have in my memory. But the thing is this, okay, there should be a trade-off. It looks like, okay, why don't we load as many processes as possible in my memory? Let's load 100 processes. That's going to make my CPU utilization very favorable, very nice. Why don't I load 100 processes in my memory? Then question for you. Why don't I do that? Yeah.
Context switch is expensive.
What?
Context switch is expensive.
Well, we ignore the context switching, right? Let's ignore the context switching. It is very fast.
RAM size is limited.
Yeah. Well, I mean, it is not free. You cannot load 100 processes to your memory because memory is finite. You don't have infinitely large memories. It is not available. There is no such world. We are restricted. I mean, somebody is asking you, I mean, where do you get all that memory? And the processes are large. Let's look at that question now. Okay? Let's look at that question now. Let's say I have a computer which has 8 gigabytes of memory, okay, which is realistic. And I know that the operating system takes 2 gigabytes of memory by so on. So that means that I have only 6 gigabytes available for the processes. If I say that each process takes 2 gigabytes of memory, and each process is waiting for I/O for the 80% of the time, okay? So that means that I can fit only 3 processes. Each of them is 80% I/O wait time, and if I take this, okay, I cannot do better than that because I don't have any space for inside my memory. It's going to be 50% efficiency CPU utilization time, ignoring the context switch time. Okay, with this computer of 8 gigabytes of memory, I can do, with this kind of processes, I can do 50% memory CPU utilization. Okay, so somebody say that, what if I add more memory? Let's add more memory. By adding more memory, my CPU utilization will be better. Yeah, let's do that. Let's add 8 gigabytes of more memory. That's going to be what? 1 minus 0.8 over, so 8 gigabytes means that I can add 4 more processes, 0.8 over 7, right? So I can keep 7 processes in my memory. Let's go there. 7 is this, and this one corresponds to, it looks like 80%. So I became around 79 or 80% efficient. Okay, so I went from 50% to 80%, 30% gain. Okay, so by adding 8 gigabytes of memory, I gained 30% CPU efficiency, which is nice. Okay, it's kind of surprising result. By adding memory, you are utilizing your CPU more. But if you look at the formulas, that's right. Okay, that's right. So it is 30% more efficient now if you add more memory. So more memory always helps with your CPU utilization. More efficient memory. Okay, so let's keep doing this, and let's add 8 gigabytes more. If I add 8 gigabytes more, and if it gives me 30% more efficiency, it's going to be around like more than 100% efficiency. Let's do that. If I add 8 gigabytes more, so I am going to do this. 1 minus 0.8 over 11. What is this? 1180. Can you calculate this one? What is this number? Can somebody calculate this one? The guy at the back. You have a calculator? Calculate this one for me. Nobody's making any move. Just they're watching, like they're watching movies.
91%.
91. Okay. So it is 91%. So I went from 30% to 80% to 91%. Okay, so this is 8 gigabytes, 16 gigabytes, and 24 gigabytes. So at this time I only gained 11% efficiency. So after a while, adding more memory will, of course, will give you some more efficiency, but it's not going to be as dramatic as this much. Okay, so to get to the around 100%, you need to have maybe 50, near 50. Okay, there is no 100% achievable because you know the formula, right? Unless you have infinitely many processes. So the effect of adding more memory is not that much after some while. Okay, because you are very near to 100% efficiency anyway. Good. So we can do these kind of calculations because of this simple basic assumption. I am waiting for I/O. Why don't I run other stuff? That's called multiprogramming, right? Okay. So some mathematical modeling of the. Without doing this kind of modeling, we cannot know what's going to happen if I add more CPU, if I add more process on my system. Okay. So there's the cost of the multi-programming, ignoring the context switch time. And context switch time is okay because, again, maybe most of the time I can ignore the context switch time for this case. Maybe I'm going to do the switching. Maybe I'm going to do the switching 1 or 2 times per second, and I can tolerate that one for this kind of, assuming that it is not interactive. If it is interactive, then the context switching is going to be a lot. Because to keep in, let's say I have 10 processes, okay? The thing with the interactive processes is this. They are very, very I/O bound. They wait for something to happen. For example, Microsoft Word is very interactive process because it waits for me to type something, or it waits for me to scroll the window, it waits for me to do something. It really does very CPU bound stuff. Even the spell checking and etc. It is not that much CPU power, right? So there it waits. Okay, so what does that mean? It means that it is spending most of the time it is blocked, but time to time it is waken up by the operating system says that something happened. And to stay interactive, it has to take the CPU and check if something needs to be done. So it has to be even though it is waiting for something to happen, it has to be scheduled very often. That's the thing with the interactive processes. They have to be scheduled very often. That means that their context switch time is a lot. Okay. Whereas at the other hand, let's say I have a batch process. It is printing the tickets for an airline company. Okay, it is not interactive, but it is waiting for loss of I/O. Take the data from the disk and send it to the printer, etc. No interaction. No, you don't have to switch this one a lot because it doesn't need any interaction. It doesn't need any responsiveness. Okay, so maybe this kind of a CPU utilization calculation is valid for batch kind of processes, but not other kinds of processes. Anyway, so we did that, and there it is. Okay, any questions up to this point? Usually in real life, we do these kind of calculations not based on these kind of formulas, but based on simulations. Okay? What is a simulation? I make a dummy process that keeps the CPU busy for 20% of the time. Another dummy process that keeps the CPU busy for 30% of the time. Okay? And I run all of these processes on my operating system. The operating system that I am designing, developing, and I check the overall efficiency by looking at the process table entries and the CPU utilization, etc. Instead of running these kind of formulas, I just do the simulation on a virtual environment. You know the virtual environment, right? It's like an environment that you are going to build for your homeworks. Or the virtual environment that I showed you about the hypervisors. Do you remember the hypervisors? Hypervisors are like piece of software, but they act like a virtualized hardware, right? So those hypervisors, they can know what kind of CPU utilization or memory utilization you have on your system. Okay, so simulations are preferred way of doing these kind of calculations. Okay, so any questions so far? Okay, nobody's asking any questions? No, I need a question at this point. If there are no questions, then I am going to get that attendance sheet, choose somebody's name, and we'll make him or her ask me a question. If that person is not here, then that's going to be another issue. I need a question. I need many questions. Yes.
As count of processes goes to more cache misses.
More, the higher number of processes cause what?
More cache misses.
Page misses?
Cache misses.
Since invalidation, because of invalidation.
Well, I mean, if you is that the question? More number of processes cause more cache misses. Yeah. Well, that's the context switch penalty, right? I mean, if you have, yeah, you are saying that this formula is too simplistic. Okay. By putting more processes in your memory, it's going to cause you loss of context switches. Loss of context switch means that every time you make a context switch, your cache will be invalidated. And cache invalidation means that loss of cache misses. Yeah, that's true. We ignore that problem with this one. Okay. More than cache misses, we have much more serious problem in our hands. It is the page misses, page faults. Okay. Page fault is this one actually. We don't use this picture that I painted here. We don't try to fit all of our programs in our memory. We keep some of them, some parts of those processes on the desk. Okay, I showed you how many processes I am running on this stupid small computer, right? I am running almost 100 processes. If I add them up, it's going to make maybe 1 terabyte of memory. I don't have that kind of memory. I have only 8 gigabytes of memory on this one. Okay, so most of those processes are kept on the desk. If I switch to that process, I need to load that data from the disk to the main memory. That's going to be a lot slower than, a lot worse than cache misses. So more than cache misses, page faults is our problem. For many processes. Okay, so the picture is not as rosy as this. This one says that as long as you have the memory, put more process in your memory. No, if you do that, that's going to cause loss of page faults, and loss of page faults means that trashing. We are going to talk about this trashing. Trashing is that operating system is busy loading your pages, moving your pages back and forth in between the main memory and the disk. And instead of doing useful work for me, it is doing lots of trashing instead of doing page loading and unloading, etc. Okay. So your main point is valid. I mean, there is no such thing as this curve is going up and up and up until it hits the 100% mark. No. Context switching is going to make our life a lot difficult, and I cannot talk about it 100% in detail because you need to know some stuff about the memory virtualization too, which is the next chapter. Yes?
Sometimes block stage happens when we are trying to write or read from disk. But you said we are writing our processes in a disk. How this is efficient, or is this efficient?
Well, it is handled with the help of the hardware actually. Okay, if the scheduler says that I am going to pick this process now, it is time for this process to run. Operating system says that okay, process, it is your turn. But when the process starts running, it says that okay, I'm going to access this memory location. And the operating system again realizes that that memory location is not in the memory, it is on the disk. So again, operating system has to load that data. So it is all handled by the operating system. Process doesn't know that. Process doesn't know that it is on the disk. Process doesn't know that it is not on the memory and it is on the disk. Operating system handles it. And they have invented very nice ways of doing this in 1960s, again, paging. When we come to paging, I think I can give you a better answer for your question. Again, I mean, so these are very simplistic approaches for modeling multiprogramming. Without giving you the whole details of memory virtualization, I cannot talk about both sides of this trade-off. So let me move on with this chapter then that means that we need to be quick to go to the memory modeling. But before that, we need to finish up with this chapter, the processes and the threads. Okay, so I keep talking about the threads a lot, processes and threads. So processes and threads are very, very related. We said that I can have multi-processes on my memory, multi-processing, multi-programming computers. Yeah, we know that. But there is the other idea of threads, okay? Like processes, threads are programs running in parallel, okay? More than one thread running on my computer. So each thread is an execution, but unlike the processes, okay, threads, they share the same address space and data. Okay, what does that mean? It means that, okay, each process has its own address space. Each process thinks that it owns the whole memory. Okay, I can do whatever I want with my memory. I don't have to report anything about my memory to anybody else, and etc. That's the assumption about the processes. Thread says that, okay, I am sharing this piece of memory with some other threads. Okay, so the same address space and data is shared. Why are we doing such a thing? It is because it's so efficient. Okay, if you share your address space with somebody else, then the context switching is going to be a lot faster. Why? Because there is no cache invalidation. You are using the same address space. It's going to be the same data, right? What else? It's going to be fast because if I am sharing my address space and data, a lot of this page table entries will be the same. Okay, so my memory management, all the stuff will be the same. If I am sharing these files, these are all will be the same, and many things about the process management will be the same. So switching from one thread to another thread is much faster than switching from one process to another process. Okay, that would be the advantage. That's why we say that if you use multi-threading instead of multi-programming, okay, your overall system will be 10 to 100 times faster to create, to work, okay. Of course, this assumes that if you are writing a multi-threaded program, okay, we assume that most of your threads are not CPU bound. They are blocked most of the time to wait something to happen. Let's say I have 3 threads. Each of them are maybe waiting for the I/O for 80% of the time. Then multi-threading is going to help you because remember, for this chapter we are going to assume that only one CPU is available. Okay, if each of your threads or each of your process is CPU bound, if they need the CPU all the time, then multi-programming will not give you any advantage, right? Multi-programming has advantages if your threads or the processes are not CPU bound but I/O bound. Okay, and this one, there is no protection between the threads. Well, this is kind of expected. Why? Because the threads, they share the same address space. Okay, so if this is my process and if this is the memory for that process, these are my threads, 3 of them running at the same time. So each of them can access any part of this memory. Okay, so they are sharing it. So there is no protection between these threads. This is my process. Inside my process, I have thread number 1 and thread number 2 and thread number 3. And these are my memory location. These are all shared. Okay, so thread number 1 can do whatever it wants with this memory, and same for the thread 2 and thread 3. There is no protection between the threads. You might say that, well, is it a security problem? No, it is not a security problem because this process is designed and implemented by the same programmer, by the same developer. So they put these three threads not to compete with each other, but cooperate with each other. So threads, they cooperate, they don't compete, they help each other. They know that T2 and T3 is there to help me, okay? They are helping each other, okay? Processes are different. If I have this process P1, okay, and if I have created another process P2 and another process P3, let me make them P3 and P2. P1, P2 and P3 are competing with each other, okay? Each of them, they think that they have the whole computer for themselves. They can do whatever they want. But within P1 or within P2 or within P3, there are multi-threads happening, multi-executions are happening, and these executions, okay, they know that, let me make this like 2-thread process, and let me make this a 4-thread process, okay? And each one knows that the other threads are there and they are helping each other. There is no protection between T1 and T2, but there is protection between P2 and P3, okay? So processes are more, but how do I call them? Processes are more, they are heavier, they are more complicated, they are expensive to start and terminate and execute and etc. switch between. But they have their advantages too because they can provide the security. They can provide protection between them. Okay? So that's the kind of the difference between threads and processes. It's a very classical question, operating systems related question about what is the difference between the threads and the processes. This is one of the biggest differences, okay? You write multi-process systems not to cooperate with each of the processes, but to compete with them, okay? If I am running an Excel program on this one and Word program on this one, okay, Excel and Word are in competition to use the system resources. They both want to be more interactive, they both want to use more memory, they both want to use more CPU. But within the same Excel program or within the same Word program, okay, there are 2-3 different threads running. One of the threads, for example, we are going to see for the Word program is dealing with the screen management, okay? How should I look so that my user likes me? The other thread is responsible for doing the keyboard input, mouse input, and that kind of stuff, input output. Maybe the third one is there for to do spell checking, okay? So each one is doing something, but they know that the other threads are working there too, okay? So they help each other. There is no protection between the threads. The threads cooperate and they do not compete, and these are very unique features of these threads. These are actually what makes the multi-threading more efficient than the multi-processing, because context switch time is so fast, so convenient. Okay. Any questions up to now? Yes.
How threads are scheduled in the same process?
How are the schedules are threaded? How are the threads scheduled? Well, thread scheduling and process scheduling are very similar, but since their concepts are different, there are some differences between them too. And in a few minutes after the break, I'll talk about scheduling of the threads. Any other questions? Okay, good. Let me take a 15 minutes of break. Please open the windows while you are out. Let's keep the classroom empty. Let's be here around 11:44.
Tek input alıyor.
Takım kutular yazabiliyor mu?
Ne?
Takım kutular yazabiliyor mu?
Aynen. Çok tatlı, çok kısık, az da bir kodu olan tatlı vardı ama Görürsen de. Şöyle ısılayım. Gel kışın ısıt. Yine ama çok yaş veriyor ya. Gel. Bir pencere. Direkt zank diye kanka. Sonra hemen veriyor. Belki çıkarmam. Sonra çıkaramam. Buradan üst katta çok var mı? Dolapta var da onun böyle. Okula. Pandemiden önce. Okula. Okula. Bakar mısın? Var ya. Abi sıfır ayakkabı yani. Nereye gitsin? Güzel mi? Bolca onlar çok kanka. Ama bu bölgelerin hepsi devletten olmuyor mu? Bazılarından ama bazılarından tamam, şey var. Çok süper. Banka mı? O bankanın üstüne gelirini vermezse evet. Ne? Gelirini vermek mi? Evet, yaşta girme hesabından gösterebiliriz. Görme hesabı gösterelim. Başka bir dediğimiz zaman başka bir hesabı da bu. Sıkı bu an hesabı. Benim var mı yerinde? Evet, benim şu an hesabımda 50 lira falan var. O konuya nasıl aldık ya biz? Anons olmaz dersleri. Dersleri şu an ama. 10 Haziran. Haziran olamaz. Ne? Birinci üçüncü mü? O birinci üçüncü var mı? Sıfırdan dolayı mı yapıyoruz oğlum? Şu an yapıyor musunuz? Yapıyor mu? Kim yapıyor? Hiç gözükmüyor. Yapıyor gibi. Neredeyse. Yazılım hızlı bir şey yapmıyorsun.
Salaya okulda şeyler var. Farklı konuda.
Evet, çok zor. Getirin size getirin size MSP protokolüyle bir zaman MSP protokolü MSP. Aynı kullanıyor. İğrenç. Golang. İğrenç. Değil mi Coşkun? MSP protokolü severdim kanka.
O siktir yapma çok.
Bu arada bir şey diyeyim mi? Şimdi sen yaparsın. O zaman bilgin yetmiyordur ama şimdi sen yaparsın. Yok kanka, göre yapamam. Göre yapamam. İğrenç bir şey bu. Evet, çünkü. İğrenç. Çok kötü bir şey.
Beni çekip durma, beni gönderiyoruz.
Pix aldım. Gözümün hepsi. Aynı ev neymiş ya? Olmuş. Hapsi bırakalım. Bizim artık şey yapmamız lazım oluyor. Biz ne gibi ikiniz misiniz? Biz seviyoruz. Osman pazarlama.
Osman
Çok güzel, çok kafamda kanka ya. Hiç aklıma gelmemiş bu. Ya da kaç özeceğiz? Çok güzel. Acayip güzel. Unutmuşum. Jango. Görünce bayağı o köylü gibi. Jango.
Kaç tane var? Üçe başladınız mı?
Önce ben kapat.
Gebze.
Ne var ya?
İkili de çok sıkıntı.
Niye?
Mesela setlere bir değişiyorsun ya. Atıyorum setlere bir değiştiriyorsun. Setlere bir setlere üç şey sanırsın. Aynı setlerlerin içinde atıyorum hepsi işte kelime elime kullanıyor. Ne olmalı? Mesela bir şey.
Hayır, o senin oradan
Sıkıntılar var. Ya sırayla değiştirsek.
İkisini ayağına mı değiştirmek lazım?
Sırayla değiştirsek olur mu? Bilmiyorum işte.
O zaman kaç koyduk ikisini ayağına yapmaya çalışıyorum.
Sırayla yapsak nasıl olacak? Değiştirirken. Değiştiremiyorum.
Master'likte aynı hafızaya erişebiliyor. Aynı anda yapacağım, hangisini önce yaparsın? Aynen. Bir doğru etkileştirmelerde eğer o zaman içilir.
Valla bir şey söyleyeyim
Yani aynı şeyi virtual ortam kullanıyoruz zaten. Sıkıntı olmaz. Virtual ortam kullanıyoruz. Orada olmaz ama.
Ama işte eski
Yok ben bunu AMD CPU için yazdım. Çalışması lazım. Dinlemeyiz tabii ki.
Hocam özellikle virtual kurun demediniz değil mi?
Efendim?
Özellikle sanal makine kurun demediniz değil mi? Hani doğal olanlar devam edebilir hep ama.
Öyle çok zor olur ya.
Şöyle çünkü sistem dersinde de hoca dedi ki virtual'da eski yıllarda sınıflar oluyor ödevlerde. Doğal kurun dedi.
Onu hocanıza sorun. Bu derste virtual olmazsa zor olur. Biz onu virtual'da test edeceğiz.
Yani ikisini aynı anda mı kullanmamız gerekecek? Normal ve virtual. Yoksa ödev full virtual'da olacak.
Ödev verdiğin zaman oradan bakarsınız, tamam. So this is again these are the basic differences between the threads and the processes. Let's see a few examples. Let's see a few examples that are directly from the book. Actually, I talked about them, but let's see them in more detail. That will make these kind of differences clearer. Okay, so the first example, a word processor with 3 threads, again like Microsoft Word. I have this process, the process, okay, let's say it is W, word processor, and inside this process I am running 3 threads, 3 programs in execution. One program is responsible for keyboard and mouse interfacing. Okay, whenever somebody presses a keyboard button, this one takes it. It says, okay, somebody pressed it, or this one also says that somebody scrolled the mouse and etc. This one is responsible for formatting the screen, showing all the characters, all the windows and menus and etc. And this one is responsible for taking a backup from time to time, because it is very important to keep backups of your data. So every 5 minutes maybe, this one says that I am going to take a backup of your data, whether you saved it or not. Okay, so this is a typical usage of multi-threaded application development. Many processes, many threads, they are helping each other. They know that this one knows that somebody is dealing with the keyboard input output, etc. And this one also knows that I am safe because somebody is taking the backup. I am not doing those, but somebody is taking it. Okay, so each one knows that the other threads are helping myself to accomplish our final goal of coming up with a nice word processor. Okay, this one might say that I know that I am not the only thread on this process, but I know that I use too much CPU time. Maybe I should let the other threads take the CPU because they are waiting for the CPU. So this one sometimes voluntarily gives up the CPU, says that, okay, I am blocking myself. This one says that. In multi-process programs, usually you don't do this kind of stuff. You don't think about the other processes. You say that, okay, I'm only responsible for this process. I don't care what the other processes are doing. If I am using too much CPU time, it is the responsibility of the operating system to stop me and schedule some other task with the other one. You don't have a face mask? You don't have a face mask? You don't like face masks? I don't like them either, but we have to use them, please. And nobody is warning other people. Please, be more sensitive. Okay, so that's one scenario where we are using multi-threaded applications. Another one is maybe this is more typical, web server. What's a web server? Web server is, as the name implies, a server. It waits for the network connections. Okay, let's say I'm the web server of the Gebze Technical University. Thousands of people can connect to my web server. They are asking for pages. Somebody may ask for the page of the mathematics department. Somebody is asking for the page of the cafeteria. Somebody is asking for the news pages of the Gebze Technical University, and somebody has to answer them. So this is how they structure it. There is one main thread. It's called dispatcher thread. Okay, this dispatcher thread is waiting for network connections over the web. Whenever a new network connection comes, it takes the request and it hands over this request to one of the worker threads. There are many worker threads available. They are just blocked and waiting. And this one just takes the request and hands it off to one of the worker threads. And these worker threads are responsible for getting the whatever is requested, the data from the disk or from the cache, whatever, and sending it to the client. Okay, so this one is always looking for new connections, and these ones are doing the real thing, real loading of the data, and sending the results to the client. Okay, so this is a web server. Again, this is a process, PS, server process. And well, remember, in this one I have only 3 processes running. This one sometimes I might have more than 100 processes running, because if I have more than 100 people connected to my web address at Gebze Technical University, so there might be more than 100 worker threads running in parallel. Okay, I think the book has a pseudocode for this setup. Okay, the dispatcher thread is running this loop, and each of the worker threads is running this loop. So this one is run only one of the threads, but this one is run many of them. So let's look at the dispatcher loop. dispatcher loop, dispatcher thread says that get the request from the web and an address, okay? So you get the request says load the web page of the Department of Computer Engineering, right? That's the request. So I get the request. I maybe allocated some buffer for this request, and I hand off this work to one of the threads, available threads, okay? So this thread takes this work, okay? Wait for the work. It just takes the work, okay? And it says that what is this work? What should I do? Load the web page for the Department of Computer Engineering, and send all that information to the client. Okay. So first I am making a search in my cache, memory cache. If I have loaded this data before, then I don't have to load it from the disk. So I can give this directly from the memory, which would be much faster. So look for page in the cache. Okay. If it is available there, then I am going to use it. Otherwise, if the page is not in the cache, if the page is not loaded yet, I load that data from the disk, and I just return that page. Okay, so this is as simple as what a worker thread does, and this is the dispatcher thread. It makes the web server life a lot easier doing this kind of work. Why didn't they make these? Okay, question for you. Why don't make these a separate process? Instead, they made this structure in a multi-threaded architecture. What would be the disadvantage if I use a different process for each of these threads? Yes?
You cannot share memory.
You
easily.
cannot share. So what is the advantage of sharing memory?
We are serving a website. We are taking data from the same source, probably.
Yeah.
And humanity.
The answer is, if this one loaded the data from the disk for the Department of Computer Engineering into the memory, and if this one is serving the same request again, instead of these two are loading the same data from the disk to the memory to separate locations, this one says that if somebody else loaded the same data to the memory, then I'm going to use it. So they are sharing the data available in the memory. So that means that it's a better usage of the memory. It is better usage of the time, because reading it from the disk will take some time. So these worker threads especially, they need lots of cooperation, because to answer the request of the similar data, the same data, they need to share data in the memory. If I have implemented this as a multi-process program, then each one has its own memory space. There are no cooperation between them. The life would continue as before, but things would have been a lot slower, a lot more inefficient. Okay, the same thing is valid about the memory utilization between these two threads, because this one says that put your data in this buffer. Okay, so they are sharing the same buffer, and whenever that buffer is not used anymore, that buffer is available for other worker thread to use it, right? Okay, so that's the thread use. So for these kind of cases, instead of using multi-processing, okay, multi-process architecture, use multi-thread architecture, because you need to help each other. Question for you, okay? This is my hardware, this is my operating system, okay? And I have two people using this computer, so I have to make two shells, shell number 1 and shell number 2 for two users, right? Can I make these two shells two different threads of the same process, or should I make each of the shells a separate process? Should I use a separate process approach or a separate multi-threaded approach for this kind of case? Who said that? Yeah. Why separate processes?
Because there are different users. They shouldn't use the same memory address.
Yeah. Well, using two different threads in the same process would be much efficient, but they are two different users. They have their own private data. If I let them share the same address space, they will see each other's data, and that will be bad. That will not be good. So for this case, multi-process architecture, software architecture is much preferable, even though there will be context switching consequences on it. But I mean, if I am going to make this sacrifice on those privacy, security, then what is the point of using multi users on the same computer? So that's why. So we don't say that multi-threading is better than multi-processed applications. We don't just say the opposite. It depends what you are using. Okay, if the threads are helping each other, there is no protection issue between them, then use definitely multi-threaded applications. They are much faster. But otherwise, if you are competing with the other processes, if there are security issues, privacy issues between the processes, then use the multi-processes. And we know how to make more than one process. Just use fork function, right? Make a system called fork, and that will make you another process. I didn't show you how to make a new thread. That's the topic for your systems programming course. But I'm going to show you a few examples, very simple, primitive examples about the multi-threaded applications. Previously, I showed you a shell program which calls the fork function for each new task. This one is going to use multi-threaded application, and it will come in a few minutes. Okay. So threads are, well, I mean, I think I'm going to skip this one. There are many ways to construct a server. Okay, there are many ways to construct a server, but the one of the best ways is using the multi-threading. Okay. Well, one might ask this: how come we don't have any privacy issues here? I mean, if this thread and if this thread are using the same address space, and these requests are coming from the two different users, isn't that a privacy issue? The thing is that no, because these threads are the threads, very simple threads. I mean, they are not telling anything about who is accessing these pages, right? They just say that, well, somebody has loaded this data and you are asking for this data. This data is public already, so I'm going to give this data. So these threads are not giving out any information about who else accessed this data from what IP address, right? Okay. Well, of course, I mean, that's not my intention, but if these kind of systems are hacked, okay, if these kind of systems are hacked, then they cause lots of privacy and security issues, okay? So designing a server, these kind of servers, is a very delicate process. You need to be careful about efficiency. On the other hand, you need to be very careful about your privacy too. Okay. Yes.
What about accounts? For example, I have I logged in my account.
Yeah.
I have my personal data. What about this?
Well, I mean, for the web pages, you don't have any account information. You just connect to that page. You give your IP address and that's it, right? You don't give it. For the email servers and that kind of stuff, but things are done differently, not like this. Okay? For the email servers, for the CPU servers and file servers, things are a lot different than this. Okay? You have to be careful in that too. So this is the most basic. Privacy doesn't make any difference here case. Okay, so again, multi-threading is a very common way of writing these kind of servers, but sometimes you need to do multiprocessing too. By the way, there are other problems process. In this case, let's say this is one process, right? Process server. This is a process word processor. Okay. Let's say this thread caused a segmentation fault. Okay. Operating system says that, okay, this process caused a segmentation fault and I'm going to terminate you, right? And the same thing here again. Okay. If one of the threads causes a segmentation fault, or one of them by accident tries to access the I/O registers, then this whole process is going to be terminated by the operating system. Well, you must say that, well, I mean, I have 100 threads and one of them is crashing. This is crashing the whole process, whole web server. Yeah, that might happen. That's the other downside of using these kind of threads. Okay, and we will talk about these kind of problems when we talk about how we are implementing the threads. I mean, does the kernel know about these threads? Does the kernel know this as a simple process, or does it know it as this process has many threads in it, and if one of them fails, should I fail the whole process, etc.? Yes?
When we created the threads, we can detach them, and if we detach them, the thread.
So you are suggesting a solution?
Yes, in this case, even a detached thread causes a problem.
Well, as I said before, I mean, detaching a thread from the process requires a system call, and if the operating system doesn't know about these threads, then you cannot make a system call. We will talk about them. Okay, we will talk about them. So again, this classical thread model. I mean, from the first time we started using the processes, you have to have a thread, because thread means it is execution, right? Okay. For us, this is a classical process. There is a process and there is a thread running it. Another process, another thread, another process, another thread. Thread is just programming, executing program. Okay, that's the execution part of the program. Okay, well, inside the thread, inside the process, there are many things other than the execution of the program. Why? Because you have your address space, you have your open files, you have your memory configuration, etc. There are many things happening inside the process, but the execution part of the process is called a thread. So this thread has program counter, it has its stack pointer, it has its memory pointer, etc. for this thread, and this thread the same thing and same thing. They came up with this idea. They said that why don't we separate the idea of program execution with the rest of the process, and let's make it possible to have more than one thread inside the same process. Okay, so we are going to define a process like this one. A process model is based on two independent concepts: resource grouping and execution. Okay, resource grouping is having all those kind of information about a running program, and execution is the execution part of the program. If you separate them, and if we allow our system to have multiple execution units inside the process, then we come up with this thread idea. Okay, so that's why sometimes they say that these threads are lightweight processes. Why are they lightweight? Because they don't have to have all the things that a process has. Like the threads, they don't have their own address space, right? Threads, they don't have their own list of open files. Threads, they don't have their own user privilege stuff. Okay, so these all the things that I iterated, they all defined for the processes, but not for the threads. Okay, so these three threads inside this process, they are sharing many things with this process, and whenever you make a new thread, you don't have to create all the other stuff for that thread. That's why it is very efficient to start and continue. Okay, what else? Yeah, we talked about this. I think this one is directly from the book, that's why I put it in here. There is no protection between the threads because you don't have to have a protection between threads. The second thing is, most of the time, depending on your library, it is not possible. Okay, it's not possible to say that your address space is this much and you are protected. Okay, the second thing is that you don't have to say that. Okay, that's the reason why you are having threads. And the threads, of course, they can share the same set of open files, child process, and etc. And if one thread opens a file, that file is available for the other threads inside the same process. Of course, we are not saying that. Okay, of course, we are not saying that. Okay, this process 1 and process 2, these two threads, of course, these two threads, they don't share any memory or files or any other thing. Okay, they only share stuff within the same process. Between different processes, threads, they don't share anything. I hope that's clear. Okay, so this picture is nice. Okay, so what is shared between the threads and what is not? All of this stuff, okay, they are all valid for a process. Each process should have its own address space, global variables, open files, child processes, alarms and signals, and account information, program counter, register, etc. But each thread within a process, it has its program counter, register, stack, and state. Okay, so these are unique for each thread, but all the threads within the same process, they share all this information. Okay, so minimal number of things. Program counter, of course, if I have a different execution, I should have my own program counter. I should know where I am executing, right? Also, I should have my set of registers. Also, I should have a stack. Why is it important for me as a thread to have a stack? Because if I have a stack, I have my local variables. If I have my local variables, I can run any function that I like. Okay, I can run any function that I like. Also, state, I mean, each thread could be ready or running or blocked, right? It's like the processes. And in fact, if I have a single CPU, only one thread can run at the same time, right? The rest of them are either blocked or ready. Only one of them is using the CPU. So other than these, the rest of the address space and the global variables, they are all shared. They are all shared. Okay, so that's the classical thread model. Okay. So let's say I have a function f. It takes a parameter a, and inside this function a, I have another parameter b. I don't know what it does, and it just returns. Return. Okay. This function is already implemented. It is in my process. Okay. Two threads can call the same function at the same time, and they won't affect each other's running. Why? Because each thread has its own stack space. Remember, this parameter, these local parameters, okay, local variables, they are all kept on my stack, right? That's why whenever I make a new function called f, remember recursion, whenever I make a recursive call, on my stack, there is a space for the parameter and there is a space for the local variables. I know that, okay? So, doesn't matter how many threads are calling this function, it is fine. Why? Because every time a thread calls this function, these local variables and the parameters are stored that thread's stack. That's why each thread should have its own stack. Okay? Since I have my own registers and the program counter, then I should be fine running all these function f's in parallel without affecting each other. So, okay, very nice idea. Very nice idea. Well, at the cost of sharing the address space and no protection, but that's something that I want already. I mean, that's not a disadvantage for me for this case. Good. Any questions about threading? So only this part is shared. This part is not shared between the threads, and many things are not shared. Okay, many things are shared. That's why it is very easy to switch between the threads. In fact, some of the CPUs, many of them, they make it easy to write multi-threaded applications because what did we say for a 32-bit CPU? Okay, there are 32 registers. Okay, plus the program counter, stack pointer, and etc. For each thread, you have to have your own copy of these registers, right? That's the thing. So context switching between the thread means that taking a backup of all of these registers, keeping it in your thread table, and when you come back, you load them back. Most of the time, hardware will tell you that, okay, I will give you 8 set of 32 registers. Okay, I have 82 times 8 registers actually, and each of them can be used by a different thread. Okay, so switching from one set to another set is just a simple machine instruction. So the hardware automatically takes the backup and loads it for you. So the context switching is very, very fast because you don't have to store these registers in your main memory. Going to main memory is expensive. Working always on the CPU register is fine, and CPU will make this possible. And sometimes, well, they are not calling this directly, but sometimes it is called hyper-threading. Hyper-threading. Okay. Some CPUs, many CPUs support some form of hyper-threading. They say that I am like 8-way multi-threaded, 16-way multi-threaded, and etc. Okay, they will help you do that kind of stuff. They don't help you much in terms of multiprocessing because keeping the data for each process is very expensive. You cannot keep all that data. I mean, the list of open files and their privileges, etc., is not that easy. But keeping this kind of data for a thread is easy, and that's why with the help of the hardware it is very easy to write multi-threaded applications. Okay, good. Let's move on. So this is a classical thread model. I have a process, one process. We represent processes like a big circle. Inside the process, I have 1, 2, 3 threads, and each of the thread, it has its own stack space. Okay, each of the thread has its own stack space. So this is a classical thread model, and these are classical process models. Okay, so each process has its own address space and a single threaded execution bar. But no, this says that okay, there is a process and there are 3 threads of execution. Okay, I think that from the picture it is clear that there are no processes without any threads. Each process should have at least one thread, right? Because process means that a program is in execution. If you are executing something, then you need a thread. Okay, if you put more than one thread inside the same process, then that's called a multi-threaded process. So in a way that it doesn't make much sense to ask a question, what is the difference between threads and processes? Well, I mean, you would say that, first of all, I mean, you cannot talk about a process without a thread. So, I mean, that question is not that valid, but if you are asking me about what is the difference between having a multi-process program and multi-threaded program, then maybe we can talk about it. Okay, so these are the POSIX standard ways of creating threads. terminating them, initializing them, etc. There are many details of it. I am not going to talk about it. It is your systems programming course. You create a thread. You exit from a thread. You wait for other threads. You be nice. You tell that, okay, I use too much CPU time. I am going to let the other threads use my CPU now. Pthread yield. Okay. Well, this one is kind of fork, right? Well, it's not exactly the same, but for the process is fork. This is terminate process. Okay. This is wait PID. Remember that one? There is nothing that corresponds to this one exactly for the processes, because processes don't yield, right? Processes don't say that I am going to be nice. I am going to let the other process use the CPU now. No, you don't say that, okay? So, but for the threads to work, you definitely should use this one, okay? These are two helper functions that will initialize your thread structure and that will destroy your thread structure. Attribute init and attribute destroy. Okay, let's see one example of thread, very stupid and simple example of multiple thread program. Okay, again, you are not going to see any fork function calls on this one. Okay, I have a very simple function, print hello world. Okay, print hello world. It just takes a void pointer, whatever it is, just a pointer, and it prints hello world greetings from thread, and it just puts this TID. That's the idea of having void pointers, right? You don't have to specify the type of the parameter, etc. It looks like whatever you are passing to me as a void pointer, I am going to use it as an integer, so it will work because it's a void pointer. As long as I send the integer as a void pointer, it will be printed like an integer. And then it looks like I am going to run this as a thread, this function. And at the end of this one, I just pthread exit. I am going to terminate this thread. Okay, I am going to terminate this thread. Okay, so I am going to make this thread, and let's see how I am going to make this a thread. It looks like I am going to make 10 threads. I am going to run them within this function, within this process. Main. Somebody has called main. That means that it's a process now. Okay, process is running. I make 10 pthread structures. Okay, I made 10 of them. Status and I. I is from 0 to number of threads. In my main thread, I printed this message, main here creating thread number I, and then this is the one that creates a thread. Okay, I am going to create a thread. I am going to use this the element number I from this array. Let's ignore this null now. A function pointer. Okay, so this thread is this function actually. So when this thread runs, it's going to run this function. And as a parameter to this function, I am going to pass this I as a void pointer. This is C. I can do whatever I want. Doesn't make much sense, but I am sending this I as a void pointer because I mean, this is how you do it, okay? You specify a function name here. You specify a function name here. Okay, that's one thing. And you send your parameters as a void pointer. That's the definition of prototype of this pthread create function. Okay, so you need to send a void pointer. So I converted this I to a void pointer. I send it, but this one uses that void pointer as a integer. That's fine. So this one creates a thread, and that thread starts immediately running. Okay. When it runs, okay, when it runs and when it returns its status, I get the status back. If it is not 0, then there is a problem occurred. Otherwise, I will be fine. Okay. By the way, this one, okay, you are going to see this. You are going to see 10 main here creating thread number something something. You are going to see 10 of these hello world, okay, and hopefully you will not see any of these. You will not see any of these. Sometimes things can happen if I don't have enough number of resources to create all these threads. You might see that problem too. But I am not sure the order of the things that I'm going. I mean, thread number 1 might work later than thread number 3, or main here creating thread number 3 might come after hello world. This is thread number 1, etc. Okay, these are the surprises of the multi-threaded or multi-process programs. It is out of your hand. I mean, it is up to the operating system how to schedule these threads. That includes the main thread too. Okay, because they are all running all together using the same CPU. Depending on the scheduling decisions, thread number 7 might work earlier and terminate earlier than the main thread. Okay, or later it's going to be terminated. We don't know. So write this one. It is directly from the book. Okay, figure 2.15. Write this one, make it run, and make it run many times. You will never get you will mostly get different order of executions most of the time, and that's going to be our main problem for the rest of this chapter, because these will create sometimes, most of the time, race conditions. I mean, up to now, without running the parallel programs like this, it is all sequential, right? Assign 5 to A, then print it on the screen, then get this one. And I don't know the order. Now I don't know the order because I have 11 threads, including the main thread, and I don't know in what kind of order they are going to be running and what kind of order they are going to be terminated. And that might create lots of problems if I like to communicate between these threads. Okay, that's called the inter-process communication problem. And again, the rest of this chapter will be about inter-process communication. Good, I think, as always, I used too much of your time. I am sorry for that, but you know the rules. Okay, are there any questions? There are no questions. I will continue tomorrow morning. Please watch those videos, read the book, and come back like that with more questions. And thank you. I'll see you tomorrow.